This meeting is being recorded.
Today we are going to prove that every PID is UFD. That is, every principal ideal domain is a unique factorization domain. That is, if an ID, if we are given an integral domain D, in which every ideal is principal ideal. That is, every ideal in D can be generated from a single element of D. Then every non-zero non-unit element of D can be uniquely factorized in terms of irreducibles or primes. So we have seen similar result in the case of fx. Let f be a field, then the set of all polynomials with coefficients from the field f square bracket x. Fx is an integral domain, and we have seen that fx is a unique factorization domain in sums to 1. So in this portion, we are going to see that every PID. So earlier, fx was a PID and fx was a UFD. We are going to use the same procedure in this case as well. So we will start with the lemma. In a PID, if P is an irreducible which divides AB, then P divides A or P divides B. In the case of fx, what we have seen earlier is that if P of x is an irreducible polynomial in f of x, fx, and P of x divides f of x into g of x, then P of x divides f of x or P of x divides g of x. So in the case of f square bracket x, fx, in the proof of fx being UFD, we have used a similar lemma. So here as well, we are going to use a similar lemma. So how do we prove this lemma? So we start with a PID. Let D be a PID, a principal ideal domain. Every ideal in D is a principal ideal. And P in D is an irreducible. And P divides AB. So we start with a principal ideal domain and an irreducible which divides a product of A and B, where A and B belongs to D itself. So P divides AB means AB belongs to the ideal generated by P, since AB is a multiple of P. P divides AB means AB is a multiple of P, and therefore AB is an element in the ideal generated by P. And we know that if P is an irreducible, we have the earlier result. We have proved that if P is an irreducible, then the ideal generated by P is a maximal ideal in D. So ideal generated by P is a maximal ideal, and every maximal ideal in a domain, integral domain, is a prime ideal as well. Therefore, the ideal generated by P is a prime ideal, and in a prime ideal, if AB belongs to that ideal, then one of the factors should be there in that ideal. That is, if AB belongs to the ideal, if belongs to the prime ideal, then either A belongs to the prime ideal or B belongs to that ideal. So A belongs to ideal generated by P means A is a multiple of P or P divides A. B belongs to ideal generated by P means B is a multiple of P or P divides B. Therefore, we have the proof. If AB belongs to ideal generated by P, then P divides A or P divides B. Now we can extend this result to a finite product. Suppose P divides A1, A2, A3, etc. A product of finite times. Then we start with the initial case two times. P divides the product of 2 times A1, A2, then P divides A1 or P divides A2. From this result, we can take A equal to A1 and B equal to B A2. We have this result. So we have this proof. Now we assume that it is true for k times. Let k be any number. Let it be 2, 3, or 4, 5, any number. Suppose P divides A1, A2, etc. AK implies P divides A1 or P divides A2, etc. or P divides AK. P divides at least one of these k times. Suppose it is true. And we start with this case. Suppose P divides A1, A2, A3, etc. AK plus 1. So if you look at this thing, you can see that this product can be split into two. A1, A2, etc. AK and AK plus 1. So P divides by this or by the earlier lemma, we can show that P divides A1, A2, etc. AK or P divides AK plus 1. Now we have just assumed that If P divides A1, A2, etc. AK, then P divides A1 or P divides A2 or P divides AK. So substituting that result, we get P divides A1 or P divides A2 or P divides A3, etc. P divides AK or P divides AK plus 1. So the result is complete. So for a finite product, if P divides that product, then P divides at least one of its factors. Now we are going to give an alternate name for the irreducibles. A non-zero non-unit element P in an integral domain is a prime if P divides AB implies P divides A or P divides B. So we are giving another name to the irreducibles. So every reducible will be a non-unit element, and a unit element or element with multiplicative inverse will never be an irreducible. Okay, never be a prime. So now we are going to prove the main result. Every PID is a UFD. So earlier we have proved fx is a UFD. So here in this case, we know that fx is a PID and fx is a UFD. So this is a generalization of that result. So f square bracket x, capital F square bracket x was the set of all polynomials or integral domain of all polynomials with coefficients from the field f. So fx was a PID and fx was a UFD as well. So now we are going to prove that every PID, this result is true. So we start with a PID D. Let D be a PID. And we are taking an element which is neither zero nor a unit. So A is an element in D which is not zero and which does not have any multiplicative inverse. Then we have proved earlier that A has a factorization into reducibles. We have proved using ascending chain condition. So A can be written as product of irreducibles or product of primes. A equal to P1, P2, etc., PR. Suppose A has another factorization, A equal to Q1, Q2, etc., Qs. So we change the index to show that the number need not match. When we assume number does not match, then we prove that the number should match for any A in the domain D. So the number should match and the irreducible should be associates. That is what we are going to prove. So we are going to say that a factorization is unique except for associates, units, and order. Order does not matter. If we write 6 is equal to 2 into 3 or 6 is equal to 3 into 2, both are the same. Or if you write 6 equal to minus 2 into minus 3, this is again the same factorization. So we are going to say that the factorization is unique except for order, associates, and units. Even if you multiply with a scalar, or we can say element from the field, if x plus 1, if we can write x something like x plus 1 into x plus 2 into 2. This is a factorization. We can write the same thing as 2x plus 2 into x plus 2. Both the factorizations are the same because 2 is a unit in the field. Unit and multiplicative element, but an element with multiplicative inverse because it is from the field. So constant times in the polynomial space are units. So this was the case with fx. Here we are going to have a wider space. Here we have units are different form. We may have units of different form, but we treat them the same way. So if we have a factorization A equal to P1, P2, P3, etc., PR, and another factorization Q1, Q2, etc., QR, then we know that P1 divides A because A is a multiple of P1. P1 divides A. Therefore, P1 should divide this as well. P1 divides Q1, Q2, etc., QS. P1 divides Q1, Q2, etc., QS means this is a finite product. Then P1 must divide one of them, at least one of them. If P1 divides one of them, we rearrange the terms and we call it Q1. Maybe P1 divides Q3, but we bring it to the front. We make it Q1 and we switch Q1 to Q3. Then we have P1 divides Q1. So we can rearrange the terms once we find a number which is a multiple of P1. Then P1 divides Q1. Okay, we can write, we need this for every other time as well. We need some Q2 for P2. So we will be rearranging the whole time. So P1 divides Q1 means P1 is an associate of Q1, or these are associates. P1 and Q1 are associates because Q1 is also irreducible. Q1 cannot afford to have another reducible factor. Okay, P1 has Q. If we write Q1 is equal to P1 into some P2, then Q1 is not an irreducible because P1 and P2 are irreducible non-units. So if P1 divides Q1, then Q1 should be a multiple of P1, but the term which is multiplied to P1 should be a unit. Otherwise, it will violate the definition of Q1. We have taken Q1 as an irreducible. Therefore, Q1 should be, if there is a fact, if Q1 can be expressed as product of two terms, one of them is not a unit, P1 is an irreducible, which is not a unit, then the other term should be a unit. And if the other term is a unit, then we call them associates. That is the definition of associates. So P1 and Q1 are associates, or U1 is a term with multiplicative inverse. Then we can write P1, P2, etc. PR equal to, instead of Q1, we can write P1U. And by cancellation law, in integral domain, we can cancel times. So we don't have multiplicative inverse for P1. We cannot multiply with P1 inverse and remove those terms, but we can cancel in integral domain. Integral domain, we can cancel P1 and we will get P2, P3, etc. PR. The product of these R minus 1 times is U1 into Q2, Q3, etc. Qs. Again, we know that P2 divides this value. Therefore, P2 should divide this value. Then there should be a Q2. This is that P2 divides Q2. We can rearrange the terms again. Okay, so there exists a Q2, which is P1. There exists a Q2 such that P2 divides Q2. Again, the same result. Q2 is reducible, P2 is reducible, so they are associates. Then there is a U2. So we can do this for all the terms in P, this product. We can then we can cancel P2, and we can continue this process, and at the end we will get PR equal to U1, U2, etc. UR minus 1, PR, UR, QR plus 1, QR plus, etc. Okay, QR plus 2, etc. QS. Okay, not QR plus S, it's QR plus 2, etc. QS. Then again we can cancel and we will get U1, U2, etc. UR, QR plus 1, QR plus 2, etc. QS equal to 1. Or this is a unit, an associate of a unit or a unit. Therefore, a unit cannot afford to have an irreducible factorization. One cannot be written as a product of two irreducibles. It will violate the definition of irreducible as well. Then irreducible will have, if I can write QR plus 1 equal into QR plus 2, etc. QS is equal to 1, then QR plus 1 have multiplicative inverse, which is QR plus 2, QR plus 3, etc. QS. This is not possible because it is an irreducible and does not have any, it is not a unit and it does not have any multiplicative inverse. So we cannot QR plus, these terms should not exist. That is, S should be equal to R. Otherwise, it will be a violation. It cannot become a unit if there are reducibles in its factorization. So R equal to S. So the number of times are the same. If there are two factorizations, then both the factorization into irreducibles will have the same number of times. And we have seen that if there is such a factorization, then P1 is associated with Q1, P2 is associated with Q2, then the factorization is unique except for associates. Of course, we can change the order and we can add units. There will be units because P1 is an associate of Q1, then there will be some unit making the terms equal. So the factorization is unique except for order, associates, and units. Now we are going to prove that integral domain Z is a UFD. We only know this thing because we have seen earlier that any integer can be uniquely expressed as a product of prime numbers. In the case of Z, the primes we already know. 2, 3 are the primes in Z because these are the irreducibles in this integral domain. In Z, we are going to prove using the earlier theorem. So first we need to prove that Z is a prime ideal domain. Z is a prime ideal domain because every ideal in Z is of the form NZ. Every ideal in the form Z is of the form NZ, where n is a natural number or n is an multiples of n. If 3Z means multiples of 3 minus minus from minus infinity we can write etc. -9, -6, -3, 0, 3, 6, 9, etc. So these the multiples of 3 are the ideal generated by 3 and it is 3z. So every ideal in Z is of the form NZ and all the ideals are prime ideals. Therefore, Z is a PID, prime ideal domain. We already proved that every PID is a UFD, therefore Z is a UFD. So without using any other result related to primes, we can prove this theorem using our lemma and this proof. So this is the fact we already know, but we are proving this as a result of, as a consequence of this theorem. In the next video, we are going to say that if we have a UFD, then the polynomial space built on that integral domain will also be a UFD.